All right, so 24 says that we have a light bulb and it's filled with gas. That's how they work. And the atmospheric pressure when the light bulb, or the, oh, well, hold on, I'm saying more. I'm saying, my brain's reading the words faster than I can say them. So, the gas in the light bulb is at atmospheric pressure, right? So, there's that one atmospheric pressure. That'll be something we'll work with later. When it is at one atmospheric pressure, the bulb has a temperature of 20 cc's. So we'll call that T1 because I think there'll be a final temperature. So that'll be 20 cc's, or not cc's, 20 degrees Celsius. Last class I did a bunch of liquid. Yeah, I did like a bunch of conversions. All right, so then to keep on the gauge inside the light bulb when it's hot, assuming its average temperature is 60 degrees Celsius, so that's my final temperature. And I should probably do a capital T for this. So that's 60 degrees Celsius. And so remember that we have to make that Kelvin, right? So that's going to have to be, we're going to have to add the 273 here. So this would be 293 in Kelvin. And then the final temperature, T2 in Kelvin, will be 333. And the textbook says 0.15. And so if you want to get the answer that matches the textbook, we should probably use that. Different textbooks round it differently. So I'm going to follow the textbook. Yes? Yes, quickly. And then, and neglecting the change in volume. So they're saying that there's a little bit of change in volume because there's some thermal expansion or gas leaks. So we're ignoring it. It's almost like ignoring friction when you do the kinematics. The actual final pressure of the light bulb will be calculated in part A because the gas bulb will expand. What will the actual final pressure be taking this into account? Is the difference negligible? So it's two parts. We're going to ignore the expansion of the bulb because it's glass. It'll heat up and it'll expand due to the pressure and all that stuff. And then, so that means the volume will change slightly. And so, and then does it matter? Do we need to go through all this hassle? So we're going to start with the ideal gas law, right? We're going to say P1 times the volume is equal to the number of molecules, Boltzmann's constant, T1, and then the final pressure, P2, the volume, because they said the volume doesn't, we're neglecting the change. So let's just start with this and then we'll go and do part A and do part B. Okay. So for part A, we can actually let me do this first because we do got to derive this. So if we divide one of these by the other like we did on the previous problem, and it doesn't really matter, but let's say that we say P1 V1 is equal to NK T1 over P2 be NK T2. Well, what an interesting thing that happens is that because we're neglecting the change in volume, the volume should cancel the number of molecules in Boltzmann constants. They all cancel, right? So then I have P1 over P2 is equal to T1 over T2. Okay. And then what I want, I can actually just solve for P2, the final pressure, right? So if we do some algebra, we'll do like the cross multiplying and then divide. So it's kind of called the bat and ball method. So I'm going to multiply these two numbers and then divide by this. So then my final equation will be P2 is equal to P1 T1 all over T2. And so we just plug those numbers in, right? So you also have to remember, and I forgot to mention this, remember that 1 atmospheric pressure is equal to 1.013 times 10 to the positive of 5, right? And that's in Pascal. So we need to do that conversion for our pressure. So we're going to insert that here. Yeah, that's a 1.
Wouldn't that be 2? They wouldn't multiply together.
Oh, you're right. Good catch. Sorry, I made a little mistake here. So I would have caught it when I went to plug the numbers in. So this should be P2 on the top, and this should be T1. So anyways, this stuff is equal to 1.013 times 10 to the positive 5, right? That's my P1. And times T2, which will be 333.15 Kelvin, divided by 293. And we'll get 1.15 1 times 10 to the 5 Pascal. Let me zoom back in so we can see it. That thing doesn't want to cooperate today. Okay. And so this is Pascal. All right, so that is that's just P2, right? And then for part A, we had to find that pressure. For part A, I'm trying to think. We're told that 1.38 times 10 to the 4th pascals, which is Pascal is the same as newtons per meter squared, right? That's going to be equal to 0, and that's just this conversion ratio, sort of. That's going to be equal to 0 to or equal to 0.136 atmospheres. Okay. And so that's really all we needed to do for that. So let's just reread that to make sure we're answering the question. So B, it says, let's reread the question, make sure it makes sense. Suppose a gas-filled light bulb is manufactured so the gas inside the light bulb is at atmospheric pressure when the bulb has a temperature of 20 degrees Celsius, which is like room temperature. Find the gauge pressure inside such a bulb when it's hot, assuming that the average temperature is 60 degrees Celsius. Really hot. And neglecting any change in volume. They're saying that there is volume, but not really, due to thermal expansion or gas leaks, right? So they're assuming all the gas is trapped in there. B, the actual final pressure for the light bulb will be less than calculated in part A because the gas light bulb will expand. Okay, so this is interesting. I think we did the final first, and now we're gonna do A. Because the part B of the question. So, we're gonna let, for the B part, you're gonna let the second pressure, which we just solved for this, that's what we solved for. And so we're gonna let the final pressure without the bulb expansion be P2. And then we're gonna let with expansion, we'll call that P2 prime. So this is without expansion, and with expansion we'll let that be P2 prime. And then also in that same vein, because we're going to have some way to separate these, T2 let, I hate when this thing does that. All right. Yeah, but the thing acts weird. Alright, we'll try this again. Sometimes if I write too fast, it just loses its mind. So then we're going to let T2 be the final temp. And then lastly, we're going to let V prime be the final pressure. Or volume, I mean. And that's with expansion. Okay? Alright, so how do we set this up? Well, remember that our ideal gas law, P2, regular P2, will be equal to V, or I'm sorry, P2V will be equal to the number of molecules, Boltzmann's constant, times the temperature, or T2. And then we could also find it without expansion. P prime would then be multiplied by, can somebody get the door please real quick? P prime would be multiplied by V, right, plus delta V, the change in volume. And that would also be equal to, hi, what did you need?
We're doing a fire compressor. Would you like to help out?
I'm recording a video,
Okay.
kinda, can we do it later?
Yeah.
Come back later, okay?
Okay.
Alright. And so number of molecules, Boltzmann's constant times the final temperature. Okay. And then there's a bunch of algebra you could do to derive this, right? So essentially I can plug in different things, right? I'm trying to think. P2 is equal to, so P prime is equal to V naught. Yeah. So the algebraic manipulation, I think if you take P and divide it by P prime, you can get the change in volume, right? So essentially, they're both equal to NKT2, right? Do you see that? This is going to be equal to this, and this is going to be equal to this. That really shouldn't change. So then what we have is we have P to V is equal to P prime times delta V, or V plus delta V, which is the change in volume. Okay. And what we're doing is we're saying, well, if they're both equal to NKT2, then they're equal to each other. Does that kind of make sense? All right. And then, so from there, what you could do is rearrange that and solve for P prime by just simply dividing by V plus delta V on both sides. V plus delta V. Okay, and these cancel. And so you'll end up with this P2 prime is equal to, and I'm not quite sure that why they wrote it like this, but they have it P2, and they wanted to separate that for some reason. Oh, I know why. So V plus delta V, so you got this, okay? And then there's some, you could do like some manipulation here to separate these. So this is an old trick to kind of, you have a delta V and V, and you want to separate them or pull something out. So you can divide both of these by V. So if you do that, in other words, you have the V on the top here, I can divide this by V, and then do the same thing on the bottom, divide by V. So then your next line would be P2 prime is equal to P2 all over V plus delta V, and that is divided by V. Okay? Yeah.
Are you still recording?
Yeah.
No.
So then P2 prime, I'm almost done though, is equal to, you can factor out a 1. You could distribute the division, right? So you're dividing, but you can distribute that just like multiplication. So then this becomes P2, and so V divided by V is just 1. And then delta V divided by V is just delta V divided by V, okay? And then somewhere in your formula, somewhere you should get that delta V can equal beta, right? That's from like 13.1 or something like that. Delta V times the initial volume times delta T. So this is from a previous section. So if that's the case, we'll just plug it in here and the V's will cancel, right? Or you can solve it for if I divide this by V and I divide this by V. What my goal is to substitute something in here. So when I do that, I get delta V over V is equal to beta delta T, right? And so we get P2 prime is equal to P, and I just plug that in, right? And I can say 1 over beta delta T. And so then we solve for P2. That's what part A was. That's all the P1, P2 stuff. And so we said regular P2 was just that 1.151 times 10 to the 5th. 10 to the 5th, not 2. Pascals. Then over here, to solve this one, I'm going to say P2 prime is equal to my 1.1. Oh, there's a 1 in here. 1.151. I'm trying to hurry. 151 times 10 to the 5th. Right? This should be P2. I keep.
Maybe tissue.
Yeah, somewhere. There's a box over there. And then down here I have 1 plus beta. And so you would look up beta in that chart, right, for gas. And so that number would be 2.7, the coefficient would be 2.7 times 10 to the negative 5, right? And then that has to be multiplied by the change in temperature. And so remember, it went from 20 degrees to 60, so this would be 40 degrees.
Would you change it to Kelvin or no?
It's the same either way, right? So
Oh, yeah.
yeah, that, remember I said that last time?
Yeah.
Yesterday we were talking about that. Yeah, so if you take 60 and minus 20, it's 40. But if you take the 333 minus the whatever it was, 293, yeah, it's still 40, which is kind of a little trick. So anyways, when you do all that, the pressure there would be 1.5150 times 10 to the 5 not joules. Why did I write joules? What is wrong with me? Pascals, right? Okay. So then the last part would be is what's the difference, right? So where did we define PG? I think they're talking about the pressure of the gas.
Which is 1.151 times 10 to the 5th, right?
Yeah, I think we forgot to write that down before. So let's derive PG because we forgot to derive that. Hold on. That's really easy. That's just going to be equal to P2 minus 1 atmosphere. Yes?
Can I have it? Do you have a rubber band?
No. So I would say, I do, but give me a second. I got to finish this. We're almost done. Times 10 to the 5 newtons per meters square, which is really pascals. And minus the 1.013 times 10.
Where did we get that number from?
What number?
1.013.
This is 1 atmosphere, but we converted it to pascals,
Okay.
right?
Oh.
So
yeah,
this is
okay,
in
okay.
pascals. Sometimes it's weird. The textbook writes it as pascals, but it's newtons per meter squared, right? It's force divided by cross-sectional area is pressure, right? All right. So, all right. So that's where we get our number from. So now that's important because to do part B, the last thing is we're going to compare the differences in pressure. So if we redo that again, we end up with like, and so that was the original PG, though, was I think 1.36 times 10 to the 4, right? Or
Where did we get that number from?
135 atmospheres. That's the math. That's what we subtracted it, and then if you subtract it, that's the answer you would get. Oh, the original PG was this, 1.36. Right, that was a 6. And then if we do this exact same thing with PG prime, right? That would have to be P2 minus 1 atmosphere. And so then if you do the math on this one, because it's now 1.150 times 10 to the 5th minus 1.013 times 10 to the fifth. Our final answer for the pressure of the gas is about 1.35 times 10 to the 4, or 0.135 atmospheres. So that's why we would say it's negligible, right? You can kind of, because of the system. And so that's the difference. You'd subtract those. So it's like 1/1000th of an atmospheric pressure. Does that help?
No. Well, I,
Let me stop recording before.
Yeah, can I get one?
Can you get one what?
A rubber band.
Yeah, do you have a
Yeah,
rubber band?
right here.
Is
You
my
could
hair
just
look
told me. Does my scalp look sunburnt?